Hello, everyone. It's my pleasure to give a talk in this conference. The title of my talk is Blockchain-based secure data sharing platform in Internet of Things. I'm Qin Li. This work has supported by several courses, including Professor Wenjin Lo from Virginia Tech in the United States, and also Dr. Ning Zhang and Professor Zeli Liu from Nanking University. In my talk, I will present in 4 parts. First, I will show the motivation of this work. Then, I will present our constructions for 2 schemes. And then I will show the implementation and the evaluation of this work. Finally, is the conclusion of this talk. First, let me describe the motivation of this work. As we know, data sharing is very important in Internet of Things and big data area. And also, privacy is important. So first, I will show you this problem. Then I will give some introduction on blockchain and the smart contract. Then I will show the challenges in currently. As we know, Internet of Things generates a huge amount of data, especially in 5G area. So data sharing plays a very important role for various applications. For example, in medical data analysis and financial prediction, we need to use the data sharing for the data analysis because usually only one company they cannot provide such a big amount of data for the data mining or artificial intelligence. So we need more data from different companies or entities. Thus, we need the data sharing. And also, we know if you have more data and we can train a better model to get better accuracy. And also, we know if we have more data, we can get more fine-grained data sharing and data utilization. So that's the motivation that's why we need data sharing. And data sharing, we have some challenges. For example, how can you ask other users to share the data with you? We need to find some incentive method to encourage users to share the data from like Internet of Things. So that's the motivation of this kind of work. And we know there are many different reward mechanisms, such as if you contribute your data to some company, they will provide you some coupon or other things to thank for your contribution. So this is a reward mechanism we have in currently applications. And if you want to incentive user to share the data from Internet of Things, reward data contribution is important from users. And we also know that owner controlled the data and the function is also important because if you want to control your information and if you don't want other user to use your data in other different applications, you must control your data, right? So we need to solve this problem in order to encourage users to share the data. That's the problem. And we know there are many different challenges in data sharing systems. So how to protect the privacy of data is very important. We have several different techniques for the privacy of data. For example, we have different access control to data like encryption and other no cryptographic techniques, and we also have utilization control of data. We have also many different anonymization techniques, such as differential privacy or other anonymous techniques. So even though we have different privacy techniques to protect data, it's still not enough, because we still need to realize like the fairness in data sharing. It means that even you use encryption that can protect the data privacy or security for access control, but how can you guarantee the fairness? For example, if the data is shared by the user, how can the user is guaranteed that he can get the reward from the contribution? So this is a problem for the system. Another system is how to outsource data service in cloud. As we know, IoT devices users have only limited storage and computing resources. So they usually have to rely on some cloud server or some other high performance computer to provide such kind of computation for them. So data and the analysis are outsourced to cloud by device users in order to save the computation and data analysis. In that way, for example, in this figure, you can see that first the data is encrypted and uploaded to the cloud, and we also need to analyze the encrypted data, and we can get the result to make sure that the result is correct or not. Finally, we can achieve the reward. Okay, this is the first challenge. And the second one is how to guarantee data quality. Data quality is important, as we know, in order to train some better model. We need to high quality data. First, we need to make sure that the originality of data is the first important, because the outsourced data should be from user devices. It must be guaranteed not forged by the data, right? And another problem is the unforgeability of data. As we know, data used for analysis must haven't been modified by any user. It should be original from the devices. So these are two requirements for the guarantee of the data quality. So above three requirements is the main challenges for data sharing, including privacy of data owners, fairness of the data sharing, and verifiability of the outsourced results. So this data sharing challenges in cloud for Internet of Things. Based on the above challenges, we need to provide some new construction for the above challenges. We present three different constructions in this work. The first one is basic scheme based on SGX, and the second one is an advanced scheme based on homomorphic encryption. Finally is some new PUF function with blockchain. So I will show them one by one. The first is the basic scheme based on SGX. Before presentation of the scheme, I would like to show the some concept of the blockchain and smart contract. As we know, blockchain can be viewed as a decentralization or distributed ledger for the application. And you can see the description of blockchain can be viewed as a series of blocks in a chain from block I plus 1, block I plus 2. So for each block, there is some different information, like the information of previous hash function value and some nonce, some timestamp, and the tree root. The tree can be make a hash tree in order to save the storage size like this. So this is the figure of some blockchain. Okay, and in blockchain, it's very important to build based on some secure consensus scheme. For consensus, it must be consistent and also liveness. And we also need to build the consensus maybe from different solutions. Currently, we have many different consensus. Like in Bitcoin, we use the proof of work (POW) for the consensus. In Ethereum, we have proof of stake and the POW. And others, we have PBFT, IFT, and other consensus algorithms. So this is the consensus. And we also need to some trusted execution environment for our schemes. We have different secure execution environment like TE or SGX, and we also have other open source TE like remote attestation for correctness and integrity. We also have trusted hardware and programs in enclaves. So we have different hardware and software techniques to make sure that the programs is secure run in this environment. We know in a TE, it provides a safe zone for the application. In some untrusted component application, we can make sure it's run in some secure environment, and we have data and code to be run in the trusted component and the enclave. Okay, in this way, we can make sure it's secure and nobody can get the information from the trusted environment. Okay. Then I will show our system. We call it a PrivacyGuard system. From this picture, you can see that IoT system architecture and PrivacyGuard framework, we have several layers for these constructions. In the first layer is devices. We have different Internet of Things devices, and we have in the second layer we have a network to transfer the data to the above layer is called service data agent. The data agent will encrypt the data to the encrypted storage and trustworthy data utilization. From that, we will have different entities like data owners and data consumers like Facebook and YouTube and so on. So we also need some blockchain smart contract to connect the application and the users. So this is the architecture of our system. So next I will show the architecture and the system model of our scheme. In our scheme, we have several entities like data owners, data analysis, and the cloud servers and the trusted hardware. We used SGX. And the data owners will be rewarded by the data consumers if they share the data with the consumers. And we have several security requirements. For example, the users are able to define their own access policy for sharing data, and data usage should be recorded on a platform that offers no reputation and transparency. First, I will show the algorithm of data storage in our PrivacyGuard systems. The data from devices will be encrypted before outsourced to the cloud. And then the hybrid, maybe you can use hybrid encryption by insert keys in the trust hardware such as SGX. So in this way, the data can be encrypted and stored in the untrusted cloud, and the key is stored in the SGX. Then, if we want to access control to some data in PrivacyGuard, we need to make sure the access policy is satisfied. The access policy is embedded as a smart contract on blockchain by data owners. As we know, smart contracts are used to facilitate the transaction of data and temper resilient to record of data utilization. So in this way, you can see that we have different access policy for different users. It's only defined by the data data owners. Okay. Then with the blockchain, the users, if you want to use the data, you need to pay the rewards to get the distributed data. And the users can recover the data with enough pieces. It means that the data are stored in different pieces, and only the satisfied explorers are satisfied. Then the different pieces will be combined together to recover the data for the users. And smart contract can be realized the furnace of the payment and data utilization. So this is the big picture and the algorithm of the access control for our system. Then we would like to present some analysis of PrivacyGuard. There are some advantages, such as it's very efficient and also very easy to design because we use SGX. But we have also some limitations. For example, we have the assumption that it's based on the TEE, and there is no security proof of the scheme. So this is our scheme. Then I will show another advanced PrivacyGuard based on homomorphic encryption. As we know, there are some requirements of data exchange in our IoT system. For example, we have fairness, verifiability, and reverse requirements for our data exchange IoT system. We also have other challenges with RSGX, like if you would like to verify the computation at cloud, you need to make sure the data is correct. And we also need to guarantee the privacy of the data owner. Because if there's no trusted environment, the dataset of data owner will be exposed to the operation system. So next, I will show that trusted execution environment-based and homomorphic encryption-based schemes as follows. First, the cloud is run as follows. From TE to homomorphic encryption, for the untrusted operation server to trusted environment, it requires encryption data and the response to the servers. And the response can be homomorphic encryption. So it can be use this as a secure environment. This is the architecture of the advanced PrivacyGuard homomorphic encryption system. We have different entities, like we have two cloud servers. The reason why we need two cloud servers is that we need to make sure the computation is verified. So use two cloud servers to perform the same computation. We can make sure the result is verified. And we have the data owner and the data analysis, and we also need some smart contract, okay, and also some server. Okay. So the system model and the security assumption is as follows. The data storage and its analysis are outsourced in cloud, and a result will be accepted by data exchange if the entity responsible for its verification does not raise objection against its time. And we also know the contract is trusted because of the reliability of blockchain. So this is the basic requirement. And in our advanced scheme, there is no binding corruption contract among any subset of entities, and all these participant entities are rational, and the data owner will upload its data to cloud servers, and the reward is assumed to be paid in Ethereum. So we need to make sure to answer the first question is that how to enable the analysis on encrypted data. we can use the homomorphic encryption, right? So the analysis task supported is associated with the operations by homomorphic encryption. We also make sure that data owner is supported to decrypt the analysis result in ciphertext. So in this way, we can make sure that different operation can be performed on the encryption. And another question is how to ensure analysis task is honest carried by to our server. So we need to make sure that they can compare the result. In this way, we use the ciphertext to be decrypted by data owner and then compare the two result in plain text. Okay. As we know, some malicious data owner they will return false decrypted results. So we must ensure that they will not do this because they need to be paid. So we need to make sure the result is first decrypted. This is the overview of our scheme. We need some non-interactive argument of knowledge, and the homomorphic encryption support homomorphic addition and multiplication. And 3 algorithms in our system are used. Okay. The security-based game theory is the no-binding collusion agreement should be used, and we also need some other assumptions like this. So this is a basic security requirement based on game theory. And another question is how to ensure honest decryption by data owner because it's important both to verify the results of cloud. So we propose a simple mechanism dedicated to verify homomorphic decryption. Our scheme is based on indeterminate system of equations so that to verify the results. Okay. Finally, we would like to present another techniques to ensure the data originality. We use the physical unclonable function, PUF. A PUF function is based on a physical system and very easy to evaluate, and its output looks like a random function, and so we can use it to realize the data originally. And why we use the PUF function? Because it can generate a unique secret key based on the physical system. So it can achieve very highly secure system and it's inexpensive because we need no special fabrication technique. And PUF can enable secure low cost authentication. We use the PUF as a function and a challenge. This you can see the system architecture. In the middle, we have different nodes and blockchain network. And in the outside layer, we have different devices for IoT. So the difference with the previous scheme is that for each devices, we have some PUF function to make sure the data is secure. Okay, and in this way, we have the PUF with blockchain for safe and secure IoT environment, and you can see this picture. Okay. In this way, it offers the security for data originality and also data provenance for the blockchain. And PUF function can provide a unique identity to IoT devices, and the decentralized network model offers control and trust-free operation in IoT environment. So this is the security. And we also perform the implementation of evaluation of our different schemes, and including the test bed and the parameters used in our environment. We use the Ethereum nodes to the same physical machine and other parameter you can see from our paper. So I will skip this part. Okay. And this is the result of our evaluations. And you can see we can provide a very high efficiency compared with other homomorphic encryption techniques. So it's very practical for big data. And this is the different comparison of our system with other previous work to make sure the data sharing with blockchain. Okay, finally, I will show the conclusion of my talk. In my talk, I show the challenges of the data sharing in Internet of Things, and then I present 3 different algorithms and schemes for the security in data sharing based on blockchain. The first one is based on SGX and the trusted execution environment. And advanced transaction is based on homomorphic encryption. And finally, we also present a PUF function for data originality. And then we present the evaluation performed by our constructions. So this is my talk. Thank you very much.